Good afternoon, everyone. Today we continue the course Geomechanics for Geologists, chapter number 7, Sand Production Prediction. This is a lecture plan for today, and today we will consider three topics. The first topic is problems and object of researching. The second topic is sand production models. At last is sand production management. Let's consider chapter number 1, problems and objects of researching. The regions experiencing sand production challenges in oil and gas extraction include United States, Gulf Coast, the North Sea, Russia, China, Canada, California, Venezuela, Western Africa, Indonesia, and Malaysia. As illustrated and figured in this slide, Schlumberger Company has implemented sand control technology in more than 30 countries worldwide. Sand management involves a strategy for operation in situations where conventional sand control methods are not usually utilized. It focused on effectively monitoring and managing sand influx, well pressures, and flow rates to maintain successful production rates. Over the past decade, sand control processes have been implemented in numerous oil and gas wells globally, particularly in conventional reservoirs, leading to higher hydrocarbon production rates. Sand and sandstone are two very different things. Sand is loose granular material made up of tiny particles of rocks. The sandstone is a much harder and more durable rock that is formed from layers of sand that have been compacted and cemented over geological time. One of the key differences between sand and sandstone is their physical properties. Sand has a relatively low density and low compressive strength. Sand is also highly porous, which means it could hold a large amount of water. In contrast, sandstone is a much harder and more durable rock. It has a higher density and a higher compressive strength than sand. Sandstone is also less porous than sand and can hold less water. Its interlocking texture and cementing materials make sandstone resistant to erosion and weathering. The geomechanics deals with the unstable sandstones, not from sands. The sand and sandstones share some similarities in terms of their composition, and let's consider sand classification by size, sorting, and routing. As you can see here, the classification by grain size can be divided into clays, silts, fine sands, medium sands, coarse sands, granules, and pebbles. As for rounding, we can divide this classification into angular, sub-rounded, and well-rounded sands. As for sorting, we can see the poorly sorted and well-sorted. The strength range of sand and sandstones is very different. The strength can vary from 0 to tens and hundreds of megapascals. The reasons for which is it possible to be taken out can be divided into two groups, dynamic and static. The following are related to static are purely formation consolidation, friction angle, lithology as cementing material, particle size, shape, etc. Okay. As for following are related to dynamic is fluid flow effects, depletion of reservoir pressure, production rate, increase of water production, and associated water weakening effect. Let's take a closer look at the water weakening effect. This effect is related to the fact that water flooding or deformation leads to a decrease in rock strength. To date, many mechanisms have been proposed to explain the water-induced strength reduction, such as fracture energy reduction, chemical and physical deterioration, pore pressure increase, capillary tension decrease, and frictional reduction. Several mechanisms may act concurrently to control the deformation of wet rocks. However, none of these mechanisms can be uniquely determined for the great variety of rock types, but one of some are likely more significant than others for certain rock types and test conditions. The graphs show that water saturation samples, blue column, have a low strength than rocks with natural saturation, red columns. Let's consider the study in which the natural and saturated weakly cemented Cretaceous sandstones were used to carry out Brazilian test and UCS test. And also acoustic emissions characteristics were monitored simultaneously. The main conclusions from this researching are follows. At first is water weakened the mechanical properties of weakly cemented Cretaceous sandstone. The unconfined compressive strengths of the saturated sandstone decreased to 40 and 32% of the natural state respectively. The TSTR parameter decreased from 35 and 26% compared to the natural sandstones. Also, at second, the acoustic emission energy corresponded well with the low time curve, and the failure of the samples was accompanied by the release of a large amount of acoustic emission energy. In saturated sandstone, water destroys the cementation between mineral particles, initiated microcracks in the sample, and reduces the cumulative acoustic emission energy. Also, the distribution range of the acoustic emission peak frequency in natural sandstone was wider than that in the saturated reservoirs. At third, the spatial location of acoustic emission events reflects the development of microcracks during loading. There were almost no microcracks in the saturated sandstone during the early stage of the Brazilian test, and a large number of acoustic emission events occurred rapidly near the peak, leading to the failure of the samples. However, in the process of anaxial compression due to the weakening of water, there were more microcracks in the saturated sandstone than in the natural state sandstone. Let's consider part number 2 that calls as sand production models. Let's begin and remember the transfer from coordinates of global coordinates to well coordinates. The borehole can be imagined as an opening in a plate as shown in the middle of picture. When the well deviates at any angle at azimuth, this borehole face will rotate accordingly. Okay? For any orientation of well, it's necessary to calculate the stress state corresponding to this orientation. The hole possesses inner and outer radius so large compared to inner that they can be deemed infinite. So the step number 1 is identification of principal in situ stress state. The step number 2 is defined stress state with respect to the Cartesian coordinate system attached to the wellbore. At last, step number 3, this is finding the stress state with respect to the cylindrical coordinate system. If we write down the Mark-Column failure criterion and express it in an inequality relation to the strengths of TVS or UCS, we can obtain the following inequality that you can see on this slide, where CI phi is a function of borehole stresses, elastic and properties and strength properties, If we write the distribution of SI as a sinusoid around the wellbore, then in places where SI exceeds the strength, the breakouts will be formed. In our case, this is a sand production or sand removal. The thick-walled cylinder TVS method is used to predict the sand production. The experiment consists of the following stage. First, sample preparation, a sample with a diameter of 30 mm, a length of 60 mm, and in an internal hole with a diameter of 10 mm is drilled. The second, sample is saturated with a model of formation water under vacuum. The sample is installed between stop sensors are fixed to monitor axial and radial deformation, then placed in a high pressure chamber with which filled as compression fluid. The study is carried out at room temperature. The pore line is brought out to the atmosphere without pore pressure control. As for the compression pressure, the test is carried out under hydrocompression conditions. The effective compression and axial pressure is set as 10 atmospheres. During testing, continuous recording on confined pressure, axial load, radial and axial deformation is performed. Axial pressure and confining pressure are applied to the sample, load rate near 1 MPa per minute until the sample is crushing. The failure point is registered. At the end of the test, the confining pressure is switched off. The sample is removed from the chamber and photographed. The graphs of the change in confining pressure and axial stress over the time are plotted, as well the axial and shear lateral strain from a confining pressure. If there are no TVS data, we can use unconfined compressive strength data. We talked about this methodology of the conducting UCS in previous lecture number 4. The models of sand production can be analytical and numerical. We will start from analytical model and move on the numerical models at the end of our presentation today. The most convenient forms of visualization of analytical model are triangles and well sections. Let's start with triangles. The triangle in the figure shows a safe drawdown window, which shows the predicted safe drawdown for a particular combination of completion, rock strength, and initial reservoir pressure and stress condition. The plot of bottom hole flowing pressure versus pore pressure is divided into zones. The first zone is zone if no production above the diagonal line. The second zone is zone of sand-free production, green zone. At last is red zone, where is zone of sands plus soil production. With the increase in depletion, the amount of drawdown that we can apply to the completion without failing the rock change. And one of the case goal of sand production prediction is to predict the safe drawdown line in the safe drawdown window. There are various methods for constructing such triangles. For example, this slide shows the criteria of Hattema, Weingarten and Perkins, Wilson. As we can see, in all cases considered, the slopes of boundary values between zones of different colors are different. There is also a rectangular visualization of the results of interpretation on sand removal. For example, in the FIST shell software, a graph of the relationship between bottom hole pressure and vertical effective stress is assumed, in which areas of lack of sand, transition zone with an increase of the proportional of sand, as well as catastrophic sand removal are marked in different colors, from green to red. On this slide, the following slides will show the evolution of triangles with the Wilson criteria in time. That is, we see how the drawdown changed the location in the boundary lines. Please note that already at the third time steps, that is in 2008, the yellow border has moved higher. In 2015, that is in the fourth time steps, the point falls into the yellow zone where the first signs of the solid phase in the well begin to appear. And in 2017, they already see a points in the orange zone, which is characterized by an increase in sand removal, and we see this during sand monitoring. Now let's move on to well sections. This is a similar form of visualization of the results of sand production. On the well section, it's possible to visualize SIF with an overlay of the rock strengths. The zones with SIF more strengths belong to sand outflow zone and are highlighted in red. On the other hand, when the SIF doesn't reach strength, sand removal is not observed. This is green zone. The right side shows the stratigraphic layers and year when the sand removal will begin. On this slide and below, we will consider specific examples, an analytical model of sand production. This slide shows a stratigraphical column and mineral composition model, distribution of elastic and strength properties with the calibration on the core, as well as a graph of the combined pore pressure gradient, bottom hole gradient, and minimum horizontal stress gradient. On the far right of the track, the sand removal flag is shown, where yellow highlights indicate the interval in which sand is expected to be carried out. This slide shows the same analytical model but with a change over time. Please note and pay attention how the relationship between SIF and strength of the rocks will change over time. Over time, with a decrease in pore pressure and a decrease in bottom hole pressure, SIF begins to strive for strength of the rock. If the SIF strength of the rock is exceeded, it's assumed that sand removal will begin in these intervals. Accordingly, the sand flag begins to be yellow. For example, this. Thus, the degree of sand production increases with the subsidence of pore pressure in the well. Here and after, the flag of sand removal for 5 wells at the same time is shown. The methodology developed by Sakhalin Energy and Lithosphere in the LithoStudio software allows you carry out simultaneous calculation for an unlimited number of wells. In this method, it's assumed that by changing one parameters, it's possible to observe change in the sand flag for several wells at once. The calculation is software and based on the fact that data arrays consisting of curves of the same type but having different time steps are loaded in the program. Pore pressure and bottom hole pressure data loading allow minimum and maximum horizontal stress arrays to be updated. The updated minimum maximum horizontal stress arrays, as well as the original pore pressure arrays, bottom hole pressures, are used to calculate the maximum allowable bottom hole pressure, critical drawdown pressure, SIF parameter, and sand removal flag. Here is an example of the results of the sand analysis for several wells for different formation. The cell shows the month and the year of the expected onset of sand production. Since the maximum bottom hole pressure is a function of the well trajectory, it's possible to build maps of the maximum allowable bottom hole pressure for different trajectories. On this slide we can see that 9 maps of the maximum allowable bottom hole pressure were built for the 9 trajectory of the wells. The highest values are typical for wells drilled in the SH max azimuth, as the lowest values is typical for vertical wells and wells drilled in the SH mean direction. It's also necessary to assess which parameters have the greatest impact on the maximum allowable bottom hole pressure. Thus, as we consider normally faulting regime, so we can say that maximum effect of horizontal stress influenced here. As for horizontal and inclined wells, we can see the maximum influencing of overburden gradient. Okay, let's consider part number 3, sand production management. Why sand management is important? Firstly, the disposal of removed sand is a technical and environmental problem. Secondly, the erosion of equipment caused by sand removal leads to premature destruction and failure of well completion elements, which significantly increases the cost of development and operation of the field with sand removal. Thirdly, the removal of sand leads to a decrease in the production of the main product, oil and gas. Let's figure it how we can diagnose the solid in the well. This slide shows an example of real-time monitoring with distinct blue and yellow peaks showing sand events. Real-time sanding information has a particular importance as it allowed to control a drawdown pressure with respect to sand production. The sand production can be instantaneously detected at surface using ultrasonic sand monitors, and subsequent trending enabled timely decision of drawdown and choke management to achieve maximum sand free rates for all wells. With a real-time knowledge of the wells sanding tendencies, the operator is able to optimize well test results through efficient operation of surface equipment by mitigating potential threats of erosion, sand deposition, and environmental hazards. The sand production in the wells can also be recorded using sand logging. Now let's discuss which method of dealing with sand production can be considered as priority. This slide shows well completion methods with potential sand flow operating on both cased and open hole bases. This is cased hole selected and oriented perforation, cased hole gravel pack, cased hole frac and pack, open hole screen, open hole expandable screen, and open hole gravel pack. Another method is a chemical sand consolidation. As shown on this slide, the mixture of a chemical agent and sand grains allows you to consolidate the rocks, increase its strength, and thereby reduce the risk of mining this sand during mining. Another effective method of sand control is selective perforation. Let's take closer at this mechanism. Fracture initiation can occur in different points around the wellbore if the perforation aren't aligned with the preferred fracture plane or the maximum horizontal stress. This misalignment can create complex flow path, leading to increased formation breakdown and fluid friction pressures during hydraulic fracturing treatments. When perforations are positioned near the preferred fracture plane, essentially the path of least resistance, so they help minimize or eliminate restrictions near the wellbore. To optimize stimulation, achieve oriented fracturing, lower the risk of sand production, it's crucial that perforations are properly aligned and perpendicular to the minimum horizontal stress. Now let's look at the numerical model of sand production. It works on the basis of system of equation derived of Gelikman in 2006. This equation allows us to calculate the flow rate on a liquid with sand and flow rate of the sand itself as a function of time. Thus, it's possible to carry out not only qualitative assessment of sand production, but also quantitative. This slide shows a comparison of the actual data on the sand flow rate and the calculated data on Looyeh Studio program. As we can see here, there is a satisfactory convergence, which indicates the reliability of this calculation. The sand erosion is a major problem in many production situations because small amounts of sand in the produced fluid can result in significant erosion damage. It also causes localized erosion damage to protective corrosion scales in pipe wells and result in accelerated erosion-corrosion damage. The interaction of sand particles and the surface of the equipment can be expressed for three types: plowing, impact crushing, and cutting. The objective of Shear Failure work, which I'm demonstrating on this slide, was to develop guidelines for prediction at threshold velocity and particle size below which only a small available amount of erosion occurs. Threshold velocity guidelines can help estimate safe production velocities in erosive services and serve as a tool to engineers for a cost-effective design of piping system for new well. Recent methods for prediction threshold velocities in producing well are based on penetration rate in an elbow geometry, because sections this geometry are most susceptible to erosion damage than a straight pipe section. In considerable work, a formula is proposed for computing penetration rate for various pipe geometries that contains the following expression for computing the maximum penetration rate in elbows for carbon steel materials. So it depends on many factors, including pipe geometry, size, sand size, density, flow regime, velocity, and fluid properties. The characteristic impact velocity of the particle is obtained by creating a simple model for pipe geometry. This is done by relating the erosion rates of complex geometry to erosion occurring in a direct or normal situation. The impact velocity of sand particle with a pipe wall is a strong function of pipe fitting geometry, fluid property, and sand properties, as well as the amount of fluid through which the particle must travel to strike the pipe well. A characteristic length, called the equivalent stagnation length L, is used to represent distance in the simpler direct model. The impact velocity of the particles of sand in the simple model is referred to as characteristic impact velocities of the particle. A simplified particle tracking model is used to compute the characteristic impact velocity. So this model assumes that the particle is traveling through 1D flow that is assumed to have a linear velocity in the direction of the particle motion and uses a simplified drag coefficient model. The figure that you can see here on this slide shows the results for characteristic impact velocity of the particles with pipe wall as a function of several production parameters. The following are dimensional groups for parameters. At first is Rayleigh parameters and phi parameter. This slide shows the constants used in the equations that we have considered above. Okay, this is references for today. Thank you so much. Goodbye.